Is it okay to start?
Yeah.
Okay, so we are starting the second half of the this focus week on the exact quantization, exact WKB, and resurgence. And we are very happy to have Professor Yasuyuki Hatsuda from Rikkyo University as the overview speaker of this second half of the focus week. He's going to give a talk on the quantization conditions and Seiberg-Witten theory. Okay, so let's get started.
Okay. First of all, I would like to thank the organizer for giving me an opportunity to this overview talk. And I would like to briefly explain the recent developments of how to solve some quantum mechanical system by using the n equal to supersymmetric quantum field theory. So my title is following quantization condition and Seiberg-Witten theory. So as an introduction, let me explain the development after the Seiberg-Witten discovery. In 1994, Seiberg and Witten found a very powerful method to compute the exact low energy effective action in n equal to supersymmetric gauge theory. Their work is not only important in physics, but also important in mathematics. And I would like to emphasize aspects in mathematical physics. So the prescription of his discovery is the following. First, we start with some algebraic curve, which is called the Seiberg-Witten curve. Then this curve allows us to compute the period integral. And then we get the low energy effective action that is determined by the so-called prepotential of the theory. So I would like to explain it more concretely. The Seiberg-Witten curve is schematically is given by such kind of algebraic equation. Then we can define the period integral of this. Typically, this curve is given by the elliptic curve, but we can also consider more generic case. And then we can consider the period integral for this curve, because this curve defines a Riemann surface, certain Riemann surface. So we can consider several cycles that determines the period integral of the theory of this curve. Then we consider the two kinds of curve, which I call it. One of them is a cycle, and the other is a B cycle. Then we can define some kinds of non-trivial function of F0. This is very determined by implicit way. But after computing this quantity, then we can determine this non-trivial function F0, which is called the prepotential in the theory. And the claim of the Seiberg and Witten is that this F0 gives a low energy effective theory of the theory in n equal to theory. But the original method is very implicit way. And in 2002, Nekrasov found a remarkable formula for the Seiberg-Witten prepotential. His formula is depends on the combinatorial way. So he constructed some non-trivial function. I call this function is a Nekrasov partition function. This is several parameters, but the important point is Nekrasov claims that in the special limit of this Nekrasov partition function gives a Seiberg-Witten prepotential of the theory. And the important point is that this function is directly constructed by the in the combinatorial way. So using the Nekrasov formula, we can directly evaluate the F0. without evaluating any period integral of the Seiberg-Witten curve. So these two approaches have very non-trivial coincidence of the mathematically. So, and I would like to say that the Nekrasov formula has two additional parameters compared to the Seiberg-Witten theory. There is a two parameter epsilon1 and epsilon2. And to extract the Seiberg-Witten prepotential, we take the special limit of this function. Epsilon1 and epsilon2 both goes to 0. So original Nekrasov partition function have much more information than the Seiberg-Witten prepotential. And recently, there's a very interesting aspect found. Nekrasov partition function have two parameters, but certain one-dimensional subspaces of this two-parameter space can be interpreted as certain as the kind of the quantum deformation of the Seiberg-Witten original Seiberg-Witten theory. So Seiberg-Witten theory has no such parameter, but we can turn on the one parameter as a quantum deformation parameter. And this is a special limit of the Nekrasov formula. And I would like to say that there are two interesting slices of this deformation. Originally, Nekrasov constructed Nekrasov function with two parameters. Then we can consider the several slices of this two-dimensional spaces. But here I would like to say that there are two interesting limits. One is such kind of limit. Epsilon1 equal to h bar, and epsilon2 is said to be minus h bar. In this case, the deformed prepotential is related to the so-called topological recursion. And this quantization is interesting in the mathematically. And I guess that on Friday, Iwaki-san talks about this kind of quantization and how to quantize the spectral curve, Seiberg-Witten curve, such kind of limit. But today, I would like to focus on the other interesting slice of the theory. I would like to consider the different slice of the theory. Here, one of the epsilon parameter is said to be 0, and the other is regarded as a quantum parameter, deformation parameter. In this quantization is different from such kind of quantization, but I would like to say that this kind of quantization is also has a very interesting aspects of this theory. So, and I guess tomorrow Ito-san is going to talk about this kind of quantization scheme. And I would like to briefly introduce recent result of this kind of quantization scheme. Okay. So I refer to such kind of quantization as Nekrasov-Shatashvili quantization scheme. So here in my talk, I just focus on the such kind of slice of the two-parameter deformation. Then the quantization scheme of the Nekrasov-Shatashvili is the following. We start with the Seiberg-Witten curve. This has any quantum any parameter of epsilon and epsilon2, but we impose the canonical quantization relation of the theory. We in the analogy of the quantum mechanics, we regard these x and p are canonical variable in the in usual mechanics, and we impose the canonical quantization relation. Then we are naturally impose a differential equation from this curve to such kind of differential equation by replacing this p is replaced by the differential operator because we impose such kind of quantization condition. So we can construct, now we can consider the solution of this differential equation. And as in the usual quantum mechanical analysis, we can construct such kind of WKB-like solution. Then we can generalize the original story of the Seiberg-Witten to such kind of quantized system. So let me summarize the flow of this quantization. In the original, let's recall the original Seiberg-Witten story. We start with the Seiberg-Witten curve and compute the period integral. Then we get the prepotential. We can easily generalize this flow to the quantized system. We start with the so-called quantum Seiberg-Witten curve, which is given by the such kind of differential equation. Then we consider the solution of this differential equation. P is the exponential part of this solution. Then we define the quantum period of this kind of, like this kind of integral, period integral. Now the P depends on h bar, so this period also depends on h bar. So I call this is a quantum period, this system. Then as in the original prepotential, we can also compute this kind of f. This is a function of the h bar. And the non-trivial point is that this quantum deformed prepotential is also obtained by the so-called Nekrasov-Saakashvili limit of the Nekrasov partition function. Originally, the prepotential is obtained by the epsilon 1 goes to 0 and epsilon 2 goes to 0. But in this case, the quantum prepotential is just obtained by requiring the epsilon 2 goes to 0. But epsilon 1 is fixed finite. And we can regard the epsilon 1 as a quantum deformation parameter. This is a very non-trivial statement, but at the technical level, we can confirm the such kind of quantum prepotential in this obtained in this way by compared to this direct computation of the Nekrasov function. So this is I introduced two independent methods to compute the quantum period, quantum prepotential. But now we can impart the logic. We start with the Nekrasov partition function of the theory, concerning theory. Then we can directly construct the quantum prepotential by taking the Nekrasov-Saakashvili limit. Then we use this quantum deformed prepotential to evaluate such kind of quantum period. In this picture, we do not evaluate such kind of quantum period directly. We construct such quantity from the Nekrasov partition function by using the quantum deformed period. So we can get the quantum period from the quantum prepotential. This is a very important way to evaluate such kind of period integral, because we do not construct any solution of the differential equation. We use just a combinatorial formula by Nekrasov. And in the rest of my talk, I would like to explain how this logic is used for solving quantum mechanical eigenvalue problem. I pick up two explicit examples to apply such kind of idea. Okay. So this is a plan of my talk. In the rest of my talk, I first introduce a simplest example in the n=2 supersymmetric gauge theory. I just consider the n=2 SU2 gauge theory without any matter fields. This is a very simple setup, and also the Seiberg-Witten curve is very simple form. So I would like to first explain this example in detail, but the essence is encoded in this simplest example. And then I would like to introduce my recent result with Gleb Abhinav and Alba Glash in the last year. I tried to apply this idea to more physical problem in black hole physics. So this is the second part of my talk. Okay. Please, any comment and question during my talk? Okay. Is there any questions? Okay, so let me start with the first part. I would like to start with a simplest example. I consider the n=2 supersymmetric theory with gauge group SU2, and there are no matter fields. So the theory has only the gauge fields, which consists of the vector n=2 vector multiplet. And if you are not familiar with supersymmetric theory, you don't mind about this kind of fact. But if you know the supersymmetric theory, the theory only consists of such kind of only single vector multiplet, and there are one gauge fields and complex scalar fields, and there are two wire spinner in the theory. And then the original Seiberg-Witten is constructs the low energy effective theory action of this PIML theory. And in this theory, the Seiberg-Witten curve is given by this form. P and X is a variable, two variable of the parameterized Seiberg-Witten curve, and also E and lambda as parameter of the theory. And we consider in this case, this curve, this Seiberg-Witten curve has two turning points on the real axis. And also there is a periodicity along the imaginary axis in the complex X plane. So we can consider the two kinds of period integral of this theory. And I call the cycle around the two turning point is called the B cycle. And also another independent cycle is a cycle. And in this case, so we can construct the prepotential by evaluating such kind of period integral in the original Seiberg-Witten prescription. And in this case, we can exactly evaluate such kind of cycle period integral in terms of the complete elliptic integral. So this is a simple exercise to find such kind of exact formula. So we would like to compute this prepotential as a function of the A. So the A and derivative of F0 is given by this form. So the first step is to eliminate the parameter E from these two equations. Of course, it is not possible to solve this equation inversely, but we have another parameter lambda, and if we consider the small lambda expansion, we can solve this equation inversely, order by order in lambda. And then so from this equation, we get some relation between E and A. And by using this relation, we plug this expression into this form. Then we get the F0 as a function of the A. Then the final result is such kind of form. And I think we can compute the small lambda expansion, perturbative expansion in lambda in the prepotential. And the coefficient fka are completely fixed order by order in lambda expansion. This is the original method of the Seiberg-Witten prepotential. We use the Seiberg-Witten curve to compute this F0. And I have one comment on this relation of the A parameter and the E parameter. This equation is this is the equation for the A period integral, and this equation relates the parameter of E to a parameter of A. But there is a very remarkable inversion formula of this kind of. We would like to find this relation to as a function of A, but we have the very remarkable formula originally found by Matone in 1995. This E and A is related by the F0 prepotential of F0. This F0 inst is just this kind of given by this kind of equation. So in principle, if we accept this non-trivial relation, then we can construct the F0 inst by solving this A period relation. Then we can directly obtain the instant part of the prepotential. But in my point, I would like to use this relation as an explicit formula to relate the E parameter to A by in terms of the prepotential. In this relation plays a very important role in my talk. So let me. This is a comment on the A period integral, and we would like to quantize this system in the sense of the necklace of Shatashibi. So our quantization scheme is very simple. We have this kind of Seiberg-Witten curve. Then we want to quantize this curve by imposing the, as I said before, X and P. The computational relation of the X and P is just IH bar. So we replace the P parameter, P variable is minus IH bar derivative times the derivative of X. Then this quantum, this Seiberg-Witten curve is just given by this kind of differential equation. And this is well known as the form of the Schrödinger equation in quantum mechanics. So in this case, the quantization of the Seiberg-Witten curve just leads to the Schrödinger equation with cosine hyperbolic potential. This is just sometimes called the modified Mashu equation. So in the n equal to pure supernaive theory is related to the Schrödinger equation with cosine hyperbolic potential. This is a very good point. And so we want to consider the bound state energy of this theory. So we impose the additional boundary condition of the wave function. Psi x is in L2R function. Then the mathematical statement is that how to determine the bound state energy of this differential equation. And of course, we can use the usual techniques in the quantum mechanics. For example, in the semi-classical limit, which I mean that h bar is very small, h bar is equal to 0, then we can use the so-called WKB approximation in quantum mechanics. Because this is a singular perturbation, so we can assume the WKB type ansatz of the solution. And the connection problem of the WKB solution leads to the different some Boson-Maffei quantization condition for the bound state energy. this is well known in the quantum mechanics. And I just write down the final result of this Boson-Buffett quantization condition. The Boson-Buffett quantization condition is given by some one-dimensional contour integral of the P of X. P is the classical energy. Then we impose this kind of quantization condition. This quantization condition can be regarded as the equation for energy of the theory. This E is determined by this quantization condition. And we get the discrete set of energy. And this, the important point is the Boson-Buffett quantization condition just fix this kind of discrete bound state energy in the approximate level. So we cannot get the exact answer from this kind of quantization condition. And in the WKB, from the WKB point of view, this is very natural because the Boson-Buffett quantization condition is just a first order approximation of the WKB series. So also, I would like to comment on the Boson-Buffett quantization condition is written by some monodromy condition of the solution. Okay, so let me see the Boson-Buffett quantization condition can be viewed as a monodromy condition. I just consider the WKB solution of this Schrödinger equation. This is a first order approximation and not exact solution. Then we consider the monodromy. We consider the analytic continuation of this WKB solution around the B cycle. Then we formally get the analytically continued solution from this WKB solution because this minus sign it comes from the branch cut of this root px. And also in this part gives a non-trivial monodromy of the solution. So the analytically continued solution is differed from the original solution by this factor. And Boson-Buffett quantization condition just correspond to the single valuedness of this analytically continued solution, because this condition can be written as this equation. So this means that this part is equal to 1. So WKB analytically continued solution, WKB solution is equal to the original WKB solution. We can see that the Boson-Buffett quantization condition as a monodromy condition of this kind of solution. And also, we can rewrite the Boson-Buffett condition in terms of the prepotential, because I would like to emphasize that this period integral is just the same form this integral is just related to the derivative of the prepotential. So using this fact, the original Boson-Buffett quantization condition can be written by the derivative of the prepotential. And also, we can see this equation as an equation for parameter A, and solving this equation, we get some discrete value of the A. And also, we would like to know the energy as a function of the lambda, or we would like to know the energy level, but this energy also related to the original parameter A by the Mattone relation. So using the Mattone relation, we get the energy eigenvalue by plugging this AN into the Matone relation. And I would like to say that in this formalism, only the non-trivial function is a prepotential F0. If we know that this function, then we can solve this equation. Also, we can evaluate this relation. So, if we know the prepotential, then we can solve the Boas-Sommerfeld quantization condition, and we get the discrete energy level. So this, and also let me remind this F0 is just obtained by the special limit. Also, this F0 is just given by is obtained by using the Nekrasov formula. So this is the basic idea of our approach. If we start with the Nekrasov partition function, then we get the F0 without any evaluation of the classical period integral. Then we solve the Boas-Sommerfeld quantization condition in this framework. This is a basic idea. And I would like to improve this argument, including the quantum correction. Because recall that the Boas-Sommerfeld quantization condition does not give the exact answer. It just gives the approximate value of the eigenvalue. So we would like to improve the argument here in quantum level. And the basic argument is very simple. We consider such kind of WKB-like solution. Typically, we can compute this P function as a perturbative series in H bar. I just write this solution as a formal form of this kind of solution. Then we consider the B period analytical continuation of the B cycle along the B cycle. Then the naive quantization condition is obtained by imposing the single valueness of this WKB-like solution. And then we get some kind of generalized Boas-Sommerfeld quantization condition. This is originally derived by the Dunham in a very long time ago. And so we expect that such kind of quantization condition gives the exact answer. So I would like to explain the result of this result. Okay. But there is some subtlety in this approach. That I just use a very simple generalization in the original Boas-Sommerfeld argument. Here, I just consider the formal analytical continuation of this kind of solution. But this argument is very naive. And the quantization condition of Dunham is often receives a non-perturbative correction in H bar. And so to understand such kind of non-perturbative correction, we have to consider more strict analysis. And strictly speaking, we need to consider the connection problem for the exact WKB solution. Exact means that we have to consider the Borel summed WKB solution to find the exact quantization condition. And I think that this exact WKB analysis is one of the main topics in these workshops. So just as far as I see the title of the talks of speaker in these workshops, these people probably will talk about such kind of topics. But I don't explain the detail of such kind of exact WKB analysis. But in principle, we need to consider the Stokes phenomenon of the WKB, exact WKB solution. But I just proceed to this naive Dunham's quantization condition. I would like to rewrite his result in terms of the gauge theory language. This is a final part of the final step of this analysis. So anyway, we just consider the Dunham's quantization condition. This is a very formal level, but we can use the relation between the quantum period and quantum prepotential, because in this case, we also have, the quantum prepotential is also determines the formal solution of the differential equation, like this one. So using this one, Dunham's quantization condition is written by this kind of derivative of the quantum prepotential. So then recall that this quantum prepotential is obtained by using the Nekrasov formula, special limit of the Nekrasov formula. So the prepotential of this F is obtained by this kind of limit. Epsilon goes to 0, and epsilon 1 is said to be h bar. So, so I would like to say that this quantity can be evaluated by using the Nekrasov partition function without any evaluation of the quantum period. Then, solving this equation, we get the discrete value of the a variable. Then we finally obtain we want to obtain the energy spectrum, but this energy spectrum is also is given by the quantum version of the Matonnet relation. I didn't explain the detail of this kind of relation, but very unfortunately, there is a quantum version of the Matonnet relation in this case. So if we, so that all the computation is given by this equation. So the main ingredients of this formalism is that we just need to know the quantum prepotential, and this prepotential is given by Nekrasov partition function. So if we start with the Nekrasov partition function, then we get this F and also this part. Then everything can be computed in this by solving this equation, and we get the discrete value of the energy spectrum. And we can check that this quantization condition gives a correct bound state energy of the cosine hyperbolic potential. So we can consider that this quantization condition has all the information about the H-bar correction in the theory. So this is a very good reformulation of the quantum mechanical problem in terms of the n equal to super-M theory. So let me summarize the first part of my talk. So we get a very interesting lesson from this example, exact result in n equal to supersymmetric gauge theory, especially the exact result Seiberg-Witten and Nekrasov can help us to solve the spectral problem in quantum mechanical system. So I would like to emphasize that all the quantum correction is included in this formalism by using the Nekrasov formula. Okay, this is the main lesson in the first part. And I would like to, so in the next part, I would like to apply this idea to a more complicated but more interesting problem in black hole physics. Okay, are there any questions or comments? Okay, if not,
may I just ask one question?
Yes.
It seems at present this necrosov partition function is regarded as a technical device to solve shredding a problem.
Yes.
So can it be applicable to any type of shredding a problem, or can you characterize the applicability of necrosov formula to shredding a problem?
Yeah, I'm not sure about the full detail of the full generality of this problem, but in many cases we found the counterpart of the in the main concept for given Schrödinger equation. If we found the counterpart of the supersymmetric gauge theory, then we can use this formalism by solving this problem. But I'm not sure about the full generality of the any Schrödinger equation has a counterpart of such kind of n equal to supersymmetric gauge theory. But in many cases, this is the answer is yes.
I see. Thank you.
Okay.
Just one moment.
Yes.
Andre Voros wrote on the chat, if you could show the Nekrasov formula, please.
This one? What slide?
So I still don't have. Is it this formula? So yeah, he'd like to see the partition function, the Nekrasov partition function.
The Nekrasov?
The Nekrasov? Sorry.
Yes,
Z Nekrasov.
Yeah, this is some kind of partition function of the theory.
I see. See, you don't write explicit form of the Z Nekrasov.
Oh, I see. This is a complicated combinatorial formula, so I don't write the explicit form of the. But very roughly, this function is given by the sum of the instanton expansion like this form. And this coefficient zk can be computed by using the Young the sum of the Young diagrams. But I cannot explicit formula of this kind. But for given gauge theory, matter contents of the gauge theory, we can compute this coefficient uniquely, directly compute.
I see.
Okay.
I think it's okay. It seems that Andre Ross doesn't react to your comment, but I think okay, it's okay. Let's go ahead.
Okay.
Oh, okay. He said thank you.
Okay. So let me proceed to the second part of my talk. So in the second part, I would like to apply the previous idea to more physical problem. Here I consider the black hole perturbation theory. This is a very interesting in the recent developments of the observation of the gravitational waves. So let me very brief rough explanation of the motivation. When black holes are perturbed, then we find the characteristic damped oscillatory modes, which is called the quasi-normal modes of black hole. And why this black hole quasi-normal mode is important is the following. This is because the QNM of the black hole are physically important in observation of the gravitational waves. And so this is the quasi-normal mode is directly compared to the observation of the gravitational waves. So it's very important to understand this quantity in theoretically. So I would like to explain that this problem is also related to the n equal to supersymmetric gauge theory. So this is our recent attempts to solve this problem. And the basic flow of the how to analyze the quasi-normal modes of the black hole is the following. We start with some black hole background and consider the perturbation of this kind of black hole background by linear perturbation approximation. Then we get the linearized differential equation, because originally, of course, the Einstein equation is a non-linear partial differential equation, but this linear perturbation theory, then we obtain some kind of the ordinary differential equation with the second order. Then we can consider the we require the boundary condition for quasi-normal modes. Then we have to solve the two-point boundary value problem to obtain the quasi-normal mode spectrum. So this is very similar to solve the bound state energy in quantum mechanics. So our idea to solve this problem is the following. As in the previous slide, the black hole perturbation theory leads to the second order ODE. So we look for the this kind of second order ODE in the n equal to supersymmetric gauge theory, and we consider we found that this ODE is also appear in the n equal to Seiberg-Witten theory, and so this ODE can be regarded as a quantum Seiberg-Witten curve in the sense of the Nicholas Chapter stability. And then we can use the exact result in this theory. And as I said before, as in the bound state energy of the Schrödinger equation, we can also solve this boundary value problem by requiring the quantization condition of the quantum deformed prepotential. This is a basic idea, and I would like to explain the I would like to explain the detail in the simplest case of the non-rotating black holes. So we start with here. For simplicity, I would like to consider the spectral symmetric black hole, but we can also we can easily generalize to the rotating black holes. And we consider the perturbation theory of the Schwarzschild black hole backgrounds. As you know well, the Schwarzschild metric is given by this form, and FR is 1 minus 2m over R. And M is the only parameter of the black hole. It's called the mass of the black hole. Then I don't explain the detail of the derivation, but the perturbation, I just say the perturbation is this form. The metric, we first fix a background metric, but we consider some small fluctuation of this metric. I just fix this background metric as a Schwarzschild black hole metrics. Then we consider some small perturbation of the metrics. Then the Ledge and Wheeler derives that this h mu nu is given by the linear Einstein equation, but to realize this linear partial differential equation, then we can finally obtain such kind of ordinary differential equation in the direction of the radial variable. this FR is, in principle, this FR is related to the perturbed matrix, but I cannot show the explicit relation here. Anyway, the result of the Lecce and Wheeler is that the linear perturbation of the Schwarzschild black hole leads to such kind of second-order differential equation. So we focus on this kind of differential equation. This is our starting point. And this ODE can be regarded as the Schrödinger equation. And in this setup, this omega is the frequency of the black hole. Is just in the Schrödinger framework, this omega square is regarded as the energy of the this omega square is regarded as the energy of the Schrödinger equation. And also VR is regarded as the potential. But I would like, I have to see that this equation as a Schrödinger form, we have to change the R variable to some another variable X. This FR and this R and X is related by this replacement. And then X is explicitly given by this kind of relation. Then in the X variable, the Lecce-Wheeler equation can be seen as a Schrödinger equation. So we can use quantum mechanical techniques to solve this eigenvalue problem. But the boundary condition is quite different from the previous talk. In my previous part, I just consider the cosine hyperbolic potential. So the potential like this form. And in this case, we impose a boundary condition of the bound state boundary condition, which means that we have two in this region, we have two independent solutions. One is exponential decay, and the other is exponential growth. But the bound state condition requires that we don't have any exponential growth modes. So also in the x to infinity, we also have to impose a boundary condition. There is no exponential growing solution. So in this case, we have to impose these kind of boundary condition to obtain the bound state energy. There is a very similar in the quasi-normal modes problem. In the quasi-normal modes, there are two solutions, which is one is ingoing solution to the horizon, and the other is the outgoing solution from the horizon. But the quasi-normal mode boundary condition is that there is no outgoing solution from the horizon. Also, there is in the x to infinity, we also impose the boundary condition. There are no ingoing solution from the infinity. And this is very similar to the bound state problem in quantum mechanics. This is just a 2-point boundary value problem. So we expect that this kind of problem can also be by imposing the quantization condition of this quantum mechanical system. And it is known that such a boundary condition is realized by discrete complex value of omega. And in quantum mechanical language, such kind of energy spectrum is called the resonance energy, because this resonance appear as a pole of the reflection or transmission coefficients, as I explain later. And so the quasi-normal mode frequency is in general given by the complex number and we have the discrete label. And so we would like to compute this kind of eigenvalue of this differential equation, by imposing this kind of boundary condition. So this is a problem that I would like to solve. And so, as in the previous case, I first consider the WKB approximation. And I would like to say that in this case, we also, at the leading order of the WKB approximation, we can also find the Boas-Sommerfeld-like quantization condition. So I would like to explain it. We can also use the WKB approximation to solve, analyze this system. And this is just related to the scattering problem in the potential. And so we would like to consider the, I just set the normalization of this wave. The coefficient of this wave is just 1. Then we would like to determine this coefficient by using the WKB connection formula. Then I just use the famous quantum mechanics textbooks. Then we get such kind of coefficient in the is given by this form. So using this WKB result, we can find the how to solve the problem, boundary value problem, because the quasi-normal mode bound states is just this wave is not exist. So we impose this coefficient goes to is set to be 0, and recall that the coefficient A is given by this form in the WKB approximation. Then we impose that this part should be 0. Then we get some kind of normal quantization condition of this problem. So our conclusion is that this quantization condition should determine the approximate value of the quasi-normal modes. And this is so we can say that this is a quantization condition for the resonance. And I would like to this problem in the language of the n=2 theory to see that we rewrite the Legge-Wheeler differential equation to the more convenient form. And it is easy to see that this differential equation can be written as so-called confluent point equation, because you can see that this differential equation has 3 singularity. One is R equals 0. R equals 0 is the singularity of this potential. Also, we also have the singularity is R equal to M. This is the horizon of the black hole. As in this differential equation has a singularity at the R equal to M. R equal to M is the 0 of this FR. So we also has a singular point at R equal to M. Also, you can check that this differential equation also has a singular point at R equal infinity. So we have three singular points of this ordinary differential equation, and I can rewrite this differential equation as a more convenient form, so-called the normal form of the confluent point equation. In this case, in this setup, I just change the variable R to new variable Z, and in the term of Z, the Z equals 0 and Z equals 1 is just a regular singular point of this differential equation. And also Z equals infinity is irregular singular point. And this singular singularity structure of the differential equation is called the concurrent Horn equation. So in our case, the Legge-Wheeler equation has the singularity structure of this one kind of Riemann sphere. And in the physical language, one of the regular singular point is just the singularity of the black hole, and also the other correspond to the horizon, and irregular singular point correspond to the spatial infinity. So, so this is very good for us. The Legge-Wheeler equation can be written as a concurrent Horn equation, because in this case we can easily find that the ODE for Schwarzschild black hole perturbation is also interpreted as a quantum Seiberg-Witten curve for some n equal to supersymmetric gauge theory. And our conclusion is that this ODE is equivalent to the quantum Seiberg-Witten curve for supersymmetric QCD with 3 fundamental flavors. And this is our main result in this paper. And so I would like to briefly introduce the corresponding field theory of this black hole perturbation equation. And we have to consider the n equal to SU2 supersymmetric gauge theory, but now we have to add the matter fields with 3 fundamental hypermultiplet to see the correspondence to the black hole problem. But the basic idea is almost same as the pure Yang-Mills case. And in this case, we have 1 n equal to vector multiplet, and also we add the 3 fundamental hypermultiplet. And in this case, there is QCD scale lambda and also moduli parameter. These are same as the pure Yang-Mills theory, but now we have the 3 mass parameter of this 3 hypermultiplet. So the theory is complicated than the pure Yang-Mills theory. But our claim is that the Seiberg-Witten curve of this theory it can be quantized, and then quantized Seiberg-Witten curve is just written by the form of the concurrent Horn equation. So I would like to explain this structure. The original analysis of this 3 flavor system is given by the Hanagi-Oz in 1995. But here I use a more recent result by Zenkevich, and he write down the Seiberg-Witten curve like this form. And Kp and K plus minus P is at most second order polynomial in P. So this equation is has a second order in terms of P. And so if I would like to quantize this Seiberg-Witten curve as a canonical quantization, then we get some differential equation. And this differential equation has a second order differential equation. So this is not the Schrödinger type, but we can rewrite this second order differential equation as a concurrent Horn type, like this one. So we have the 2 kinds of concurrent Horn equation from the black hole perturbation theory and also from Seiberg-Witten theory. So we compare this coefficient in both theory. For Schwarzschild case, the coefficient AI is explicitly given by this one. Also in the Seiberg-Witten side, this AI is given by the parameter of the theory. So we compare these 2 these 2 results, and we carefully choose these parameters like this one. Then these 2 equations is completely coincide with each other. So if if we identify these parameters both in black hole physics and N=2 theory, then we get the same concurrent Hoyne equation. So this is our one of the main results of this paper. And so I would like to, after we found the identification of the parameter, we would like to rewrite this Boas-Sommerfeld-like quantization condition in terms of the N=2 language. Then this integral is also can be regarded as some contour integral. And we expect that this contour integral should be written by the prepotential of the this Seiberg-Witten theory, N=3 Seiberg-Witten theory. So at the leading WKB order, we can rewrite this equation in terms of this prepotential. And but of course, this is just an approximation of the WKB formalism. So we would like to we would like to generalize this Boas-Sommerfeld-like quantization condition to the quantum corrected version. And as far as I know, that in black hole perturbation theory, the similar quantization condition has already found in 1992 by these people. So I just schematically write down their result is such kind of thing. And this kind of quantization condition is just the same form of the Dunham's quantization condition. So we can speculate this result in terms of the quantum deformed prepotential. And so the main result of this work is this quantization condition is just written by this kind of quantum prepotential. Now we have to use the quantum deformed prepotential for the NF=3 flavor SQCD. Then we get the discrete value of the cosine normal mode frequency by comparing this kind of quantum version of the Martone relation. So by solving these two equations for the with respect to frequency omega, we get the cosine normal mode frequency, and we have checked that such kind of the determined cosine normal mode frequency is correctly reproduce the known result in the literature. So this is the main result of my talk. So let me summarize my talk. I have shown that N=2 supersymmetric gauge theory help us to solve the quantum mechanical eigenvalue problem. And in the second part of my talk, I just explain how to compute the cosine normal mode frequency in the spherical symmetric black hole. But it is not difficult to generalize this problem to the rotating black holes. And in our paper, we also consider the curved black hole. We can easily generalize the curved black holes. And in this case, the ordinary ODE for black hole perturbation is also described by the quantum Seiberg-Witten curve for NF=3 case. But if we consider the special limit of the extremal limit of this curved black hole, then the one of the matter fields is decoupled, and the in this case, extremal curve case correspond to the NF=2 superambiguous theory. Also, I would like to interested in the more complicated extension. If we these are the asymptotically flat black holes, but we can also consider the asymptotically non-flat black holes. For example, if we consider the asymptotically anti-Dojita or Dojita curve black hole, then we can also found the this ordinary differential equation is also described by the quantum Seiberg-Witten curve. But in this case, there are 4 regular singular points. And so this case corresponds to the usual Hoyne equation. And this is a very good property. And this Hoyne equation is also appear as a quantum Seiberg-Witten curve for 4-flavor super-Yang theory. So in this case, I would like to solve the cosine normal mode problem of this black hole. Can be by using this formulation. And also, I would like to also comment on the ODE-like approach. Probably tomorrow, Eito-san is going to talk about such kind of developments. But in this case, the ODE, from starting by the ODE and consider the Stokes phenomena, we can also derive some kind of the integral equation. This integral equation can determine the quantum period at a very exact level. So using this kind of integral equation, we can directly evaluate the exact quantum period. Then we can solve this kind of quantization condition at the very exact level of the quantization condition. So this approach is also very interesting to develop in the development of this kind of approach. So I would like to thank the audience for attention.
Thanks so much, Hatsuda-san. So it's a very beautiful talk. And so now we open the session for the questions and comments. Also, there are some comments from Andre Boros. So Hatsuda-san, can you look at the...
Yes.
Okay.
On slide 7. Okay,
the first one on slide 7.
This one? I'm puzzled by your specific WKB. Oh. Oh, I see. Yeah, I think that this kind of form is allowed for the Schrödinger type equation. Yeah, I think that, this is very, yes, not precise. For Schrödinger type, I think that this is a correct statement, but I think that in the non-Schrödinger case, more general differential equation, I think that we should consider the WKB type solution of like this form. And I think that in general, we cannot write such kind of form. The first of the, I see. Okay. And the second question is, can the full exact WKB analysis be carried out? Yes, in our paper, we just solve the confluent Hoyne equation by our final conclusion is that such kind of quantization condition solves the spectral problem in the confluent Hoyne equation. NF equals 3 superimposed correctly reproduce the spectrum of the NF, confluent Hoyne equation.
May I ask another question?
Okay.
As long as we are interested in a quasi-normal mode, gravitational waves from black hole, presumably it is just a purely classical physics without involving
Yes.
actual
So
H-bar.
the point is that the classical differential equation can be regarded as the differential equation is the same form as the Schrödinger equation.
Okay, so my question
is
what is the small parameter
I see.
corresponding to H bar?
I just introduced this parameter is a formal parameter by hand. I introduced by hand. So this is just a formal parameter to use the WKB.
It need not be. I mean, in discussing this quasi-normal mode, epsilon, your epsilon need not be small, or is it?
No. We have to set the epsilon code is set to 1 at spline.
Oh, I see.
But nevertheless, the WKB. But nevertheless, the WKB analysis in the if I understand correctly, the work of these people is claims that such kind of WKB analysis is even in the epsilon go to the 1. This kind of WKB expansion is a good approximation.
I see. So does it mean that using the exact WKB approach, one can consider the H bar larger than close to 1 instead of small parameter?
Yeah.
Is it?
As far as I know, these works consider the WKB expansion of this quantization condition. So, sorry. This is epsilon parameter. So formally, this integral can be written by such kind of WKB expansion. Then these people set the epsilon is set to 1, and this series is truncates some finite order. But then this kind of expansion is asymptotic divergence series. So if we truncate, optimal truncation gives a good approximation of such kind of divergence series. And this depends on the significance of the epsilon. But the epsilon 1 is also some, if we truncate some order of this kind of series, then we get some approximate value of the quasi-normal modes. But here we disarm such kind of formal series in terms of the Nekrasov partition function.
I see. So do I understand correctly that the resumming the Borel resummation of divergence series appearing in the exact WKB
yes.
help you to give the correct result even at H bar equal 1?
Yes. So if you consider such kind of series, you need consider the Borel resummation to get the exact answer.
Okay, I see. Thank you very much.
I have also a question. So indeed, if you consider the Borel summation of this large P, then this function is analytic for epsilon parameter, so we can set epsilon equal to 1. However, can you calculate the explicit form of Borel summations of this function?
No, I don't. I don't perform such kind of Borel research. I don't. I have not considered such kind of Borel summation
Okay,
in
then
this
so
context.
in your calculation, you consider the quasi-normal mode of
Mm,
gravitational wave.
Mm.
Then, but if you want to set epsilon equal to 1, then you have to calculate the Borel resolved form of
Yeah,
this,
if you focus on such kind of formal series of the semi-classical expansion, but here we don't use such kind of semi-classical expansion. Rather, we using the Nekrasov partition function, we automatically resum the H-bar collection. But this function is a series of the omega. This function is expanded in omega, but we can automatically resum it in H bar at the level of the Nekrasov partition function. So we have no problem of such kind of Borel resummation. And this lambda expansion is in general in the convergent series, so there is no divergent series, and there's no problem to.
So I see.
Yeah. But yeah, if you consider the semi-classical expansion, then you need to resum this kind of series by using the Borel summation. This is the usual story of the WKB series.
Okay, and this lambda is corresponding to which parameter of gravitational one?
Or lambda is very non-trivial dependence of the roughly is the omega, m omega, but the omega is also appear in very other places. So, but I'm not sure about the physical interpretation of such kind of relation. This is just comparing of two equations.
May I ask another question?
Yes.
I'm not familiar with the black hole physics, so could you explain the origin or physical meaning of the boundary condition imposed on this quasi-normal mode?
Oh, okay, I see. I can explain. In my understanding, this boundary condition is simple because there is no wave from the black hole horizon. Inside the black hole horizon, there is no waves. So it is physically natural to impose such kind of, because we just consider the perturbation of the black hole. And after that, we how to say, we consider, we don't impose, we don't add any incoming waves in the perturbation. So this boundary condition is not natural for me to impose because there is no wave, there is no waves from the horizon, event horizon. And also in the flat case, there is no boundary at the spatial infinity. If, for instance, in the ADS black hole, there is a boundary at the infinity. So we have to consider the reflection wave from the infinity. But in the flat case, there is no boundary. So the infinite, there is no reflection waves at the infinity. So I think that this boundary condition is also should be imposed for the this quasi-normal mode boundary condition.
I see. These boundary condition follows from the original Einstein equation, I suppose.
Yes, I think so. Yes.
Okay, thank you.
Okay.
Sorry, may I interrupt here?
Yes.
Sorry, so my name is Oscar, Oscar Diaz.
Oh, yes.
I've worked a little bit on quasi-normal modes. So the boundary conditions, as in any other PDE system or ODE system, mathematically, we have all the freedom to choose
Yes,
what
yes.
we want, right?
Yeah,
So
I think so, yes.
then we have to choose, you know, in the physical problem at hand, what is the motivation to choose them. So in that sense, I would say that they do not follow from the equations of motion, or better, they follow in the sense that because this is a second order differential problem, of course, you can expand your equations of motion around the boundaries, and you will find two separate solutions, two independent solutions. So in that sense, these two green arrows appear there. But then what we do to choose which one of them we pick is a physical problem that does not follow from the equations of motion, right? So the equations of motion give you two independent solutions. Then what boundary conditions you pick, you know, if it is a Dirichlet that kills one of them, if it is Neumann, or if it is, you know, some mixed boundary condition that mix the two, it's something that follows from the physics. Let me also say here, since you mentioned it, unfortunately, I could not follow your talk from the very beginning. My apologies, but here it's 8 a.m. and I did not wake up in time, but I will review it then in YouTube. But for ADS, so for the sitter, this infinity will have to be replaced by the cosmological horizon, and we will impose what we impose in the event horizon. We want only outgoing waves. The perfect way of doing this is to move to what we call the Edit and Finkelstein coordinates, that where the original background metric is regular. And then we want our solutions to be regular in these Edit and Finkelstein coordinates. And this essentially gives this notion of outgoing ingoing waves and allows us to select physically the boundary conditions without problem. In the ADS case, the problem will be more subtle, the Kerr-ADS case.
Yes. Oh, I see.
Right? Because, because there, you know, you will have a combination, your boundary conditions will be mixed boundary conditions.
Yeah, I think that Robin's boundary condition.
Exactly.
Oh, I think
because what the criteria there is that in ADS, right, again, if we do an asymptotic expansion of the equations of motion, or if you analyze the equations of motion in the asymptotic boundary, again, we find two independent solutions. We will want to fix the boundary metric, and this is what will select the boundary conditions. But fixing this boundary metric in terms of the master scalar variable that you will use, for example, the Tchaikovsky variable that you will use or the equivalent of this Reggie-Wheeler, but with a rotation, which is the Tchaikovsky, that you will work on, you will first have to translate what the boundary condition for the gravitational metric translates into in this scalar master variable. And that will be a mixed boundary condition. So it will. So you, in a sense, you will consider both the green, the arrow that is going to the right and the arrow that is going to the left, a linear combination of the two. But again, this comes from, you know, a physical analysis of the problem, not from a mathematical analysis of the problem.
Yes.
Yeah. Sorry.
Okay, thanks. Nice comment.
Can I ask also a question?
Yes.
So when you did the, a bit later, you basically solve. You're solving for the quasi-normal frequencies, and you say that, well, in general, you're in the end you're interested in epsilon equals 1, but you do get an asymptotic expansion in epsilon, which you can do optimal truncation or anything. But because you have an asymptotic expansion, that means that you could in principle have exponentially small terms, which would be relevant if you take the epsilon goes to 1 limit. How would you see those appearing?
Yeah, I have no idea, but first I have not yet computed such kind of WKB expansion in the black hole physics, so I have no idea. But as far as I see this paper, then they just consider the optimal truncation of the WKB expansion like this one. So I have no idea how to read off the exponential small correction. But in our analysis, it seems that there are no exponential correction like this quantization condition, because we in some sense we resum the such kind of quantum period in terms of the Nekrasov partition function, and there's no. It seems that there is no exponentially small correction in our quantization condition. But to be honest, I have no idea how to see that. In general, I think that by using the exact WKB analysis of this complicated differential equation, then we conclude that there is a exponential small correction in this kind of series. But I have no idea.
Yes, sorry.
Can I make a comment?
Yes, please.
So I think that if you take the Nekrasov function and you expand around h bar going to 0, in Nekrasov function you have this bunch of log of Barn function. And in this expansion, if you re-expand it, I think you can see the exponentially small correction in h bar which appear.
In 4D supermix case?
Sorry?
4D case? 4-dimensional supermix?
Yeah, yes, in 4-dimensional. You know, in the NF equal 3 Nekrasov function, right? The expression that we are using has this log of Barn functions, right? And if you want to, you know, a Nekrasov function is exact in h bar, but suppose that you want to re-expand it in h bar. You have this log of Barn function where you have 1 plus like a over h bar and these kind of terms, right? So when you expand in h bar, I think this will generate the exponentially small correction that Ines was talking about.
I don't know such kind of.
So from what I can understand, so then the resummed result that you would get basically from the Nekrasov partition function, then actually you could see these exponentially small terms.
Yes,
so they're there, they're just resummed.
Yes, they are resummed. And this is, in some sense, is all the power of using Nekrasov function. But you could, in principle, go the other way around and then expand it, and then you will see from the Barn function in particular.
Well, I didn't know such kind of. Sorry. Thanks.
I do have another question, which is more.
Yes.
I have no idea if it's possible or not. But have you seen? Meaning, so when you did the boundary conditions that you analyzed, basically, so you have very specific boundary conditions that lead you to quasi-normal modes. But my question is there a case where that you could study that would have, apart from epsilon, an external parameter? Meaning, I guess here you have mass, but it doesn't make a difference. But where somehow there could be some Stokes phenomena happening between the two boundaries as well. So basically that you're assuming that you have a certain type of wave, another type of wave, but in principle, if you had some Stokes phenomena in the middle, you could have another, meaning the other type of wave that wasn't allowed on the side, but suddenly is allowed because of Stokes phenomena, and could change the behavior on the other boundary. I'm just wondering if there's any type of thing that you could study of this type that could still be within the framework of, you know, an exact quantization from Nekrasov partition function.
Yeah, I think, but this is similar. I think that this problem is similar to such kind of ODIM-like approach, because I think that this approach is also considered the Stokes phenomena of the period integral. So, but I'm not sure about the wave eigenfunction of the Stokes phenomena, but I think that approach is similar. Arwa, do you have some idea?
I guess you'd need a parameter, sorry, just a second. You'd need some external parameter. So you'd need a different type of black hole, that you need an external parameter that would change the behavior between the two boundaries. I don't know. Sorry.
Oh, sorry, I don't understand your question. Say
Sorry?
again, please.
No,
Please
I'm just saying that basically in order to see some such thing, you'd need some solution that would have an extra parameter that would change the behavior between the two boundaries. Meaning the horizon and the infinity somehow. So I guess I'm just wondering if you've seen such a thing, or if you thought of any of these examples would fit this profile.
I have no idea.
Anyways, it was just a out there question in any case.
Okay.
Thank you.
Well, I have another question.
Yes.
So in your calculation, what is important is there are two different cycles, A cycle and B cycle.
Yes, yes.
And both are related to each other by some equation. I forgot the name, but so this is a key,
think,
right?
Yeah, quantum Wronskian or quantum Matonian. Yes.
41 or this is also fine.
Sorry. This kind of relation.
Yes. So yes. So this A and F is two different cycles, right?
Yes. This is a B cycle period, and
okay. B cycle and A is another cycle.
Yeah.
So okay. So when we consider not genus one system, I mean, in general, when we consider much more generic potentials, then we have a lot of different cycles. And in such a case, can we do similar procedure?
Yeah. In that case, I think that there are several eigenvalue parameters. For example, if you consider genus 2, then there are two non-trivial eigenvalues. So in these two eigenvalues should be fixed by the two quantization condition.
Well, two eigenvalues. For example, when we consider triple potential, then triple is okay. Genus 2, I think. There are three different cycle, right?
I see. I think in that case, one quantization condition has several period integral. I think so. So I think in such case, I think that triple. I think that several integral, but I think that.
Also, non-trivial, I mean, non-paradigmatic cycle also exists.
Yes, I think that I'm not sure about such kind of system, but I think that to determine all the eigenvalue, I think you need all the period integral, I think. And how to say? I cannot explain in detail here, but
I know in such a case, in the case of triple potential, we can determine the quantitative condition using, appropriate boundary condition. I mean, normalized condition. So it's okay, but so this relationship between A cycle and B cycle in this slide, it cannot be obtained by usual quantization condition, but this is additional information, right?
I'm not sure about such kind of case. Sorry, I cannot understand. I cannot answer your question here. But let me discuss. Let's discuss later.
Okay.
Yeah, I can. Sorry, I cannot answer.
Hello, my name is Ivan.
Yeah.
Kosko.
Yes. I know.
Yeah, so I would like to ask you a question, maybe not well formulated, but it is known that the non-perturbative effects in systems like the Seiberg-Witten, Nekrasov partition function related to the Seiberg-Witten curve or matrix models are related to vanishing cycles of the spectral curve. That is, touching points where you have the same momenta for different coordinates, or vice versa, the same coordinates for different momenta. There are extra B cycles with A cycles which are shrunk to zero. Yes. So each such point corresponds to non-perturbative behaviors, exponential correction, which they are called instantones in 2D quantum gravity. So is it possible to use your method to find the exact quantum periods in order to investigate the perturbative corrections around these non-trivial minima? I mean, the non-trivial saddle points which are related to vanishing cycles. That is to study the perturbatively the behavior around the non-trivial saddle points, which correspond to subleading exponents.
Yeah, I think in principle, yeah, the answer is yes, but I don't. I have not yet considered such kind of effects, but I guess the answer is yes.
Maybe it's complementary to your method. I don't know.
Mm. But I'm not sure about such kind of problem. Yeah. So I cannot answer immediately. Sorry.
Thank you.
Oh yeah.
Can I ask another question as well? Like, so you were giving these examples, of rotating black holes, and have you managed to so I'm sorry, maybe it's obvious the answer, but did you? So you've mentioned that there was one in particular that you had been looking at. So is it the first one, or no? Yeah, sorry, you were talking about the extremal Kerr black hole, right? So you have the equivalent, meaning, I guess, exact expression for epsilon equals 1 for all of these, or for just some of these?
Epsilon.
Meaning, you were writing, so these are extensions. You haven't, meaning you had for the Schrödinger case, sorry. For the Schwarzschild case, you had the expression that was coming from the partition function, which basically sums everything up to epsilon equals 1 or h bar equals 1. And in these cases, do you know what these expressions look like as well? Or is it work in progress?
Yeah, I just identify the parameter of the Kerr ADS or Kerr Dojita black hole like this. I just here so far I just found that such kind of parameter identification in the Kerr Dojita case, but and n equal 4. But I don't write down the exact quantization condition in that case. This is in principle it's doable, but so far I just have found such kind of parameter identification of in Kerr Dojita case.
Okay.
So can I ask a very basic question?
Yes.
So, this kind of correspondence reminds us of the gauge gravity correspondence too, but so it's quite different from such a famous gauge gravity correspondence. This is the correspondence between the equations, both equations. And I just want your how to say guess or your speculations. So this is just a different or far from such kind of correspondence. This is just the equation correspondence.
Yeah. I think that this is just the same mathematical structure. So
I see.
I have no physical implication of such kind of correspondence. I have no idea.
I see.
But yeah.
Thank you. So it seems there is no more questions or comments. So we have some more time. So if you have, please ask questions or give comments.
Perhaps we stop recording and allow
Okay,
any.
I think it's the idea to stop recording, so we can freely talk.
First, thank you so much.
Yeah, thanks so
for
much.
the really, really nice talk. Thank you.
Yeah, very good.
Yeah, very good.
Beautiful talk.
Thanks.